This is the first module in a series on basic electrical. Many people struggle when it comes to understanding electricity and circuits. In this series, we'll give you the knowledge to confidently work on electrical circuits. This will help you with the advanced systems on the modern vehicle. This is basic electrical, so we'll start with the basics. An atom consists of a nucleus, which contains protons and neutrons. The protons have a positive charge, and the neutrons have no charge. Orbiting around the nucleus are electrons. These have a negative charge. There are the same number of protons as electrons, which makes the atom electrically neutral, or in other words, it has no electrical charge. The number of electron orbits will depend on the atom, as will the number of electrons in the outer orbit. Materials can be divided into three groups: conductors, insulators, and semiconductors. The determining factor is the number of electrons in the outer orbit. If there are 1, 2, or 3 electrons in the outer orbit, then the material will be a conductor. The fewer electrons in the outer orbit, the better the conductor. These outer electrons are called free electrons because they are not held as tightly in their orbit as the other electrons. Copper, silver, and gold all have one outer electron, so they are very good conductors. Gold is the best because it doesn't oxidize as fast as the other two. Iron has 2 and aluminium has 3 free electrons, so they are not quite as good at conducting electricity. It's the free electrons that allow electricity to flow. Looking at a charged battery, there will be an excess of electrons on the negative terminal and a lack on the positive terminal. This is known as a potential difference. When a circuit is connected to the battery, the positive terminal will attract one of the free electrons from the conductor. This will cause the atom to have a positive charge. To overcome this, it takes a free electron from the next atom. This continues until an electron is taken from the negative terminal. It sounds like a slow process, but in reality, there are 6.28 billion electrons per amp per second. The transfer of electrons will continue until there is a balance in the battery. It will be at this point that the battery will be flat and no more electrons can flow. If there are 5 or more electrons in the outer orbit, then the material will be an insulator. If connected into a circuit, the electrons in the outer orbit are held so tightly that they cannot be dislodged, so no electricity will flow. Materials such as plastic, rubber, and ceramics are good insulators. 4 electrons in the outer orbit will make a semiconductor. These are crucial in modern electronics. Depending how the semiconductors are arranged, it is possible to get them to do many things. Take a diode, for example. It acts as a conductor in one direction and an insulator in the other. It doesn't conduct as well as a conductor or insulate as well as an insulator, but it can do both. Common semiconductors are silicon and germanium. We combine conductors and insulators in the wiring. One reason this is done is to prevent the conductors from touching each other. Another reason, which is just as important, is to prevent oxygen and moisture affecting the wire. If the insulation is damaged, the wire will start to oxidize, affecting the resistance in the circuit. When doing electrical testing, don't pierce the insulation to take measurements, as this will affect the wire. There are 3 main elements that we concentrate on in electrical circuits: voltage, current, and resistance. Voltage is the force that causes electron movement. The force is called electromotive force, or EMF, and is measured in volts with the electrical symbol V. This can be compared to pressure in a hydraulic system. Voltage can also be considered a measurement of the difference in potential that exists between 2 points in a circuit. Voltage can exist when no current is flowing in the circuit. Current is the flow of electrons in a circuit. The more electrons that flow, the higher the current. It can be compared to the amount of fluid flowing in a pipe of a hydraulic system. Current is measured in amperes and its electrical symbol is I. Resistance is the opposition to current flow. The higher the resistance, the lower the current flow. It can be compared to a restriction to the fluid flow in a hydraulic system. Resistance is measured in ohms, and its electrical symbol is the Greek letter omega. There are several factors that can affect resistance. The first is material. Some will have more resistance than others. For example, a tungsten filament inside a light globe. The length of a conductor will change its resistance. The longer the conductor, the higher the resistance. Cross-sectional area also affects resistance. The greater the cross-sectional area, or thickness, the lower the resistance. The resistance of a long wire can be counteracted by using a wire with a greater cross-sectional area. The last effect on resistance is temperature. There are two different effects. With one, resistance increases as temperature increases, and with the other, resistance decreases as temperature increases. Let's have a look at these two effects. I'll measure the resistance of this light globe while it's cold. I'll now turn it on to warm up the filament. When I turn it off, I'm going to quickly measure the resistance, and you'll see that it's going to be a lot higher than it was when it was cold. It'll drop rapidly, but it will be higher. Now we can see the resistance is higher. So this is a PTC device, a positive temperature coefficient. In other words, when the temperature goes up, the resistance goes up. I'll just change the range on my meter. And I've got a coolant temperature sensor, which I'll hook up to the meter. Just give it a second for the resistance to stabilise. I'll put my hand around it. That's introducing heat into the sensor, and you'll see that the resistance is starting to drop. This is an NTC device, a negative temperature coefficient. When temperature goes up, resistance goes down. There are two theories on current flow. Conventional theory, from positive to negative, and electron theory, from negative to positive. If you watch the electrons, they are moving from negative to positive. This would be electron flow. This time, instead of watching the electrons, watch the spaces that are created when they move. The spaces are moving in the opposite direction, from positive to negative. This would be conventional flow. You can see that there's really no difference. It's just the way you look at it. It's the same as looking at a glass and saying it's half full or half empty. It's the same thing. A simple circuit consists of a voltage supply. This could be a battery or an alternator. There will be a protective device such as a fuse or a circuit breaker, and a control device like a switch or relay. The circuit will have an electrical load. This could be a globe, motor, etc. To link them together, there are connecting wires. Earth return circuits will replace one of the conductors with the body or chassis of the vehicle. This has the advantage of reducing the number of wires. This would appear to be a problem, as steel is not as good a conductor as copper. This is overcome by the size of the body and chassis. Effectively, it has a very large cross-sectional area, thus reducing its resistance. Circuits can have positive switching or negative switching. Either will perform the same task. When the switch is turned off, an open circuit is created. The circuit will stop working as there is no current flow. The size of the wire will determine how much current it should carry. This table shows the nominal and actual size and the allowable current. There is always some confusion about fuses. The rating on the fuse is not the amount of continuous current that it's designed to carry. Nearly all electrical components, when turned on, will have a surge of current. The fuse needs to be capable of carrying this current surge without blowing. Normally, the fuse rating for a circuit is 125% or more of the continuous current. Ohm's law states that it requires 1 volt to cause a current flow of 1 amp through a resistance of 1 ohm. It can be expressed as 3 separate equations. Voltage is equal to current multiplied by resistance. Current is equal to voltage divided by resistance, and resistance is equal to voltage divided by current. This triangle is an easier way to remember these formulas. The line under voltage represents a division, and the one between current and resistance represents multiplication. Let's use the triangle on a couple of examples. If we have a 12-volt battery in a circuit with a 6-ohm resistor, how much current will flow? On the triangle, cover the current symbol to get the formula. Current equals voltage divided by resistance. Current equals 12 divided by 6, so the answer is 2 amps. In a circuit with a 12-volt battery, how much resistance does there need to be to restrict the current flow to 6 amps? Covering resistance on the triangle gives us resistance equals voltage divided by current. 12 divided by 6 equals 2, so the required resistance will be 2 ohms. Using Ohm's law is not something you'll do very often, but knowing the relationship between the 3 elements is. Voltage and current are directly proportional if resistance stays the same. In other words, when voltage rises, current will also rise. If you were to double voltage, current will also double. Resistance and current are inversely proportional if the voltage remains unchanged. This means that if resistance increases, then current will decrease. Doubling the resistance in a circuit will halve the current flow. That's the basics of basic electrical. If there was any part of this that you're not sure of, go back and review it again. Once you have a good understanding of this module, you'll be ready to move on to the next one in this series. And always remember, training is the key to your success. Bye for now.